Okay. Yeah. Uh, Good evening, everyone. Welcome to the week one problem solving session of linear algebra through geometry. Okay. My name is Bhavya. Okay. I'm a PhD at IITM. Okay. In computer science department. I'll be your TA for these weekly problem sessions on Tuesdays. Okay. 6 p.m. to 8 p.m. Yeah. There's another problem solving session for this course by another TA. He's doing on Fridays. That's what I think. So there are two links. The content will be same weekly, so you can either attend the Tuesday session or the Friday session. That does not matter. Okay. So it will be discussion on the same content. Of course, the questions may be different. The ideas discussed may be slightly different, but overall the content remains the same. Okay. And okay, so you also get I'll also be uploading these notes to a particular Google Drive, and you'll also have recordings of these sessions in case you miss. But of course I would okay, one moment. Okay, so of course there'll be recordings provided, but doing a one-on-one interaction would be encouraged. So having said that, okay, let's get on with the session today. So how do these problem sessions go on? Okay. So there are questions that I have created. Okay. Questions. So I'll call them custom questions. Okay. And then there are these weekly assignments, right? So once the deadline of the previous assignment is over, I'll be discussing some of the more difficult questions. Okay. Because of course I can't do it while the deadline is still active. So these two we shall be discussing on these problem solving sessions. So thing about this week is that there's no previous assignment. Okay, the deadline of this week's assignment is still active, so I cannot directly discuss the questions there. So I'll only be discussing some of the questions of my own, but take care that the coming assignments I'll be discussing the difficult questions. But if you have certain questions that you did not understand and I did not discuss that, then please let me know. I'll be willing to discuss that during the problem solving sessions. And these problem solving sessions are actually designed so that it can help you in solving the assignment questions. So even if you have some problems of an active deadline, okay, and you want to get some idea, maybe I can help you, okay, giving you an idea. But of course, I won't reveal you the full answer, right? Okay. Having said that, maybe all the details are done. Okay. So this course, linear algebra through geometry. Okay. Of course, I won't be discussing theory in a lot of detail, only when it is required. So, but this area, this course, okay, the general idea of this course is that we focus on linear algebra, but just one moment, I'll pin. Okay, how do I unpin? Okay, yeah, I'll discuss this course. This course is discussed from a geometrical perspective. What do you mean by geometrical perspective? There is more ways in which linear algebra can be represented. Okay, but the best way to represent linear algebraic operations, linear algebraic objects, is through geometric objects. Okay, Kishore is here. Okay, yeah, Kishore Goyal was asking whether you will be coming. Okay, coming back. Yeah, so that's what this course is about. Okay, and
Yeah. Hello.
yeah, hi
Hello.
Kishore. Yeah, welcome.
Hi.
Yeah. Okay. These some but there is another approach of doing linear algebra also, and that is purely not purely but mostly without visualizing things. Okay. Using from what you call an algebraic viewpoint. Okay, you see it in terms of operations. Okay, and the other way to see it would be geometrically, like for example lines, planes, hyperplanes, etc. Okay, and this is what this course focuses on. And of course it is recommended that you see this viewpoint also, so that you gain expertise in this entire subject overall. Now, what are the resources? Well, the best book for any linear algebraic course would of course be by Gilbert Strang. I think many of you have already heard about this book. So this is called I think, okay, I'm not totally sure. I think Introduction to Linear Algebra, but it has linear algebra in its name. Okay, if you search Strang, you're done. And there are also lectures by Gilbert Strang from MIT. Okay, on there it's available on YouTube. You should check it out. Okay, you should check it out. It's really well done. Okay, it's a very legendary set of lectures, and just maybe 1-2 years ago he had actually given his final lecture of his life, and there was a lot of views in the mathematical community for that particular lecture. Okay, moving on, we'll uh, look at what we can do this week. Okay, there's not much to do, so this session will probably be shorter. Many of the things you may have already seen in college or maybe even high school. Okay, most of the things, in fact. So, but I promise you that the course will not be so simple for the later for the later weeks. Okay, it'll become slightly more non-trivial and more interesting. But for now, bear with me. Okay, so here I have the questions. Okay, so the first question: a system of linear equations can. Okay, this is a very simple question, but still I would like you to answer it. Okay, to clarify all the fundamental doubts. A system of linear equations, okay, can have one solution, multiple but finite solutions, C, infinite solutions, or no solutions. Okay, so I would like you guys to say this. Okay, there could be multiple answers. So
ABC.
okay, that is quick. Okay, okay, well, ABC. Anyone else? Amlan? Yeah?
A, C, and D.
A,
A,
C, D.
C, and D.
Okay, so there is A, B, C, and Amlan said A, C, D. Okay, good. Others? Any guesses? Hiranmay and Kishore?
So I would like to modify. I forgot to see no solution as well. Yes, so we can have no solutions also a system of the linear equation.
Oh, okay.
Yes, and however the multiple. Multiple won't mean anything. So we can have one solution, infinite solution, and no solutions. Probably B is not the right answer. So this is A, C, and D.
Okay, okay, okay. So I think, is everyone fine with that? I'll just take a screenshot of this. Yeah, Kishore?
I feel all four are the answers.
All
A, B,
four
C,
could be
D.
correct. Okay, okay. Let's see. Okay. So since, like I said, let me next page to trash. Let me add a page here. Okay. So, okay. Okay, Kishore will discuss that. Okay. So we'll look at them one by one. Okay. And since this course has is linear algebra to geometry, I'll explain it purely in terms of geometry. Also because it has not been taught to solve these equations yet, even though you may already know how to solve them. Okay. So first of all, you may already have seen in the course that you may have already seen in the course that any system of linear equations can be represented by a set of lines or planes, okay, or hyperplanes and so on. But let's only look at lines. Okay. For example, if you have something like 2x plus y equals 0, then I'm just writing, it may not look like this, but let's say this is what it looks like. Okay. And then you have 3x plus 2y equals 5. Then let's say this is what it looks like. And so let me do this one in red. Okay, this is what it looks like. And the point it meets as, okay, is satisfying both these equations. The point it meets at represents some value of x and some value of y. Okay, and for example, this is, let's say, 2 comma 2 2 comma 0 comma 2, let's say this 0 comma 2, and this represents x's value and y's value, which satisfies both the equations, which means it is at a point on this line also, it is at a point on this line also, which can only happen if it is on at the point of intersection, right? So all the values of x and y means here satisfies equation 1, and all the values on this line satisfies equation 2, which means that if it satisfies both the black equation and the red equation, it means it lies on the point of intersection, and this is said to be the solution of the equation, right? So it can always have that it has one solution. It can always be that it has one solution. For example, you saw that equation in the example in the this is, say, 3 and 3. Okay, you saw that if I plot it, okay, I should probably open a plotter, but for x equals 1, y equals 1, both these equations are satisfied, so the two lines meet at something like this. Okay. Infinite, let's look at multiple later. Okay, let's look at multiple later. What about infinite solutions? What do the lines look like in this case?
So overlapping of one line over other.
Exactly. So let's say this is what the first equation represents. The second equation also represents is overlapping with the second line. Now, when does this happen? It's very easy to describe such equation. It looks something like 2x plus 4y equals 5 and 4x plus 8y equals 10. What is similar between these two equations? This is a system of equations given to me. What is similar between these two equations?
Both same, and just the second one is the twice of the first.
Exactly. The second one is just twice equation 1. So if you plot it, so the second equation is not giving us any additional information. It is actually representing the same set of points. So both equations are actually the same thing, but in different disguises. Okay. So it can have infinite solutions also. In this case, it meets at infinite points. The two lines meet at infinite points. So those form infinite solutions, and no solutions. When can this happen?
So parallel lines.
Exactly. So if there are parallel lines, okay. Although I'm only talking about two variables for now. Okay. So parallel lines is a good example. They will never meet. There is no point that these lines meet. There's no point where they have a same set of coordinates where they meet. So this is an example of no solution. Right. Now you can always ask, like, what if there are multiple lines, multiple equations? Then okay, you can think of multiple lines. But no solution could also look like this. Maybe there are 3 lines, like this, and like this. So these intersect with each other, but all 3 do not intersect at any point. This is one example. Another example would be Okay, and another example would be something like two lines are parallel, but one of them, all three lines don't intersect. So this is an example. You could ask, what if there are three variables? Well, then you will say, instead of lines, we will be working with planes. So now there is a third axis. Okay, there's an x, there's a y, and a z axis. Okay, and then you can imagine like a plane to be here. You can imagine a parallel plane to be on top of it, like this. Okay, these two planes are parallel. There's no solution. Okay, yeah, Amlan. Oh, okay. So, but you can have you can have two planes intersecting. Okay, well, if you have two planes intersecting like this, okay, this is one plane, this is another plane, and they intersect like this, then you can see that there is a line. I mean, where do they intersect? They intersect at infinite points, right? Still, it's difficult to visualize. I think next time I do it, maybe I'll use some kind of plotting software to demonstrate it. But if you have two planes and they intersect, okay, then where do they intersect? They intersect on this infinite line, infinite number of points. So even if they are intersecting and there is a solution, there is no unique solution. There's an infinite line of solutions. So as you see, the more I increase what is called the dimension, because from 2 dimension I shifted to 3 dimensions. To gain a unique point, okay, I need to add more planes. If I add a third plane, let's say, which comes in like this, then I get a unique point. Okay, so it looks something like this. So this is what I had got, and at this infinitely many, I mean, sorry, this line, it intersects, right, this plane, and if I add a third plane here, then you get maybe a unique point here, somewhere it intersects. Okay, it may not be that I had a third plane and I get a unique solution. That may not always be the case. I just increase my chances of getting a unique point where it may intersect. Okay, may sound abstract, but we'll see later in the course how it can be used practically. Okay, now no solution. We've seen that it can have no solution. Finally, multiple finite solution. This, like Amlan said, and Goel also later said, like Amlan and Goel said, this is not true. Can you try thinking of why this may not be true? Think of it geometrically. Okay, I mean, since this course is all about linear algebra through geometry, you could argue about it algebraically, but try to think of it geometrically. Why may multiple solutions may not be true?
So like say if two planes are intersecting, so two planes would be intersecting over a line. So
Okay.
then, and if the line is a finite one, then we would be having the finite number of the points.
But an equation will, it's a system of linear equations, no? An equation will always describe a single equation always describes a infinite number of points, no?
Yes. So, I mean, and
I agree. If the planes are finite. Yeah, Kishore? Oh, yeah, sorry.
You see, let us suppose two lines intersecting. One line is a curved one, and one line is a straight line, and then they are intersecting at 3 or 4 multiple points. So that would be a multiple finite solutions.
That would be, but we are talking about what kind of equations? But yeah, I mean, your answer actually gives the answer to this question.
Is it a linear equation?
It is a system of
linear equation if it's a curved line?
Yeah,
No, if it's a curved line, if it's a curved line, then does it satisfy being linear?
Good question. That's actually the point. Yeah. So, Kishore, I forward that question to you from Amlan. If it is a linear equation, if it is a curved line, can it be linear?
It can't be, But see, the case is probably it's not totally the curved line, but a straight line. But it has some sort of diversions, maybe not exactly straight, but it is meeting both the multiple with finite multiple points.
Finite
Can't
multiple
it,
points.
yeah.
I would
But
like
yeah,
to
how can that be possible with straight? Yeah, go ahead.
So I would like to add something into the Kishore's argument that
Yeah.
probably a curved line may be approximated by the multiple number of the linear lines, and but then that would be the intersection of not in of the two lines, but then multiple number of the lines.
That's right.
Probably.
Yeah, but then that's the thing. But I
Okay.
mean, all three of you. Yeah, you sure.
Sorry, Babu.
Yeah, so Goel is saying that you can approximate that
No,
curve using several.
I agree with Goel's point of view as well.
Huh.
But see, maybe my visualization, my intuition was saying that even that can be possible, but probably based on the discussion, it's not possible.
Okay. Okay, that's
yeah,
clever
I agree.
answer.
I agree. Probably the answer two is not the right answer.
Okay. Yeah. I mean, okay, yeah. So like, okay. First of all, I would like to address the question that Amlan said that if it is linear, can it be curved? So if it is linear,
No.
yeah, exactly. If it can't be curved if it is linear, okay. So a linear, I mean, there is a reason why it's called linear equation because it forms a line, okay, a straight line. A linear equation cannot be curved. Of course, you may argue that this is something like a non-Euclidean objects which are like spheres. Okay, in a sphere, I can actually draw a straight line, but actually, I mean, they are curved from some perspective. But if I sit on the surface of the sphere and navigate it, then it is a straight line. Okay, but we are only talking about Euclidean spaces here. Okay, there are only grids. There are no spherical surfaces. Any linear equation, you plot it, you'll always get a straight line. Okay, and I would say try to prove it, but I won't get into the proof of it. But yeah, any linear equation is always straight line. Okay, now we are asking the question: can there be finite multiple intersections? So let's say I make it simple. Can there be two solutions, which means two intersections? So let us only talk about lines. Okay, let's only talk about lines, not planes. Let's say I want to form two solutions by force. Okay, somehow this is my first line. If I have my second line, it will always be intersecting somewhat like this. Okay. Once this intersects here, it extends infinitely to the top and to the bottom. And this is extending infinitely to the left and to the right. This blue line will only intersect back if it goes and curves across and then crosses this line. It needs to perform some kind of a 90-degree turn, which is not possible. And you try to prove this using some mathematical logic, okay, some algebra. But again, I want to encourage the geometric side of it, okay. So the only way to actually do this would be by using curved lines. Now the question is, if I want to represent curved lines, what should I change in the equation? What type of equations do they become?
So there should be some terms like x square. I mean, some nonlinear terms should be present.
Exactly. So non-linear. So something like higher degree polynomials or equations. For example, if you see like quadratic equations, they have this curve. Some parabolic equations, right? These conic equations, and another would be like trigonometric. functions. Okay, these kind of non-linear equations, logarithmic, then there can be multiple solutions. For example, you know that quadratic equations always have two solutions, right? So this actually says that multiple finite solutions is not possible. So linear equation, yeah.
I have two questions here.
Yeah.
So first is that what about the planes? What about the hyperplanes? The planes in the higher dimensions. So since we cannot visualize them, so how to guarantee that they are not going to intersect like a line and the curve style intersection?
So okay, so that's actually a very good question. Okay, so I don't want to get in that because this will probably come later in the course. Okay, more in depth. But how do you talk about intersecting planes? Okay, so what are you saying? Can if you talk about hypergraphs, okay, can it be that in hypergraphs it is possible to intersect at two different places? That's what you are asking, no? Well,
hyperplanes, not hypergraphs.
Sorry, hyperplanes. What am I saying? Hyperplanes. Okay. So if there are hyperplanes, so let's just talk about planes for now. Okay. So let's say I have this plane. Okay, and it is intersecting here. Okay. And so this is intersecting in this line. Now you want to ask if this plane can intersect at this plane again. Well, you'll say no because this plane needs to wrap around this and then intersect again. But then you'll say, what about this is for dimension 3? What about dimension 4? So this is when a useful idea called projections is introduced. I don't want to get into detail, but projections are like shadows on an axis. Okay, so you have your y-axis here, you have your x-axis here, and this is the third dimension, right? The z-axis. Now think of this; these two planes are intersecting like this, right? Now think of me rotating it and viewing it from the side like this to form this x. So if I slightly move my camera, okay, I slightly rotate and move my camera to this direction. Okay, this is my camera. Okay, I move. Okay, this is facing that side. Okay, so and I slightly move it to that direction. I get this x, right? So this is what you see. I slightly move it and form this x, right? And
Yes.
this is my y-axis. This is still my x-axis, and until my z-axis actually is orthogonal to my viewport, which is my camera. So I cannot even see the z-axis because I'm directly looking through the z-axis. All I see is an x. This is the blue plane. This is the red plane. Yeah, this is the red plane. This is the red plane. This is the blue plane. So using this is what is called projections, because I have actually projected this blue plane on the z axis, the screen of the z axis, and I've projected this red plane also on the screen of the camera. Okay, until I see an x. So what have I done? I've reduced this three-dimensional object to a 2D object. Of course, I'm losing some information. I don't know like what is the angle at which this turns, the planes turn, and so on. But I've reduced it to an easier perspective. So I noticed that unless this guy, this now again forms two sets of lines. Now I know how to analyze lines. Okay, unless this comes back and curves and goes through this blue line, I know that it won't intersect. So I'll use the same kind of arguments, and you'll say that okay, this okay, fine, it cannot curve and go like this. But what if I was projecting at the wrong place? Maybe at the other axis, maybe it is possible to wrap around. So I'll use the same argument. I'll project it at y also. I'll project it at x also. If I have all the projections of this particular object, then it is enough to reconstruct this particular object, even though it comes from a higher dimension. I just need more equations to describe this object, and I'll get the same argument from any angle I view. There needs to be a wraparound, okay, in order to intersect twice, which is not possible because in all the projections it's not possible for the lines to actually come back and intersect.
So what if I have an object in 20 dimensions?
In
20 dimensions, say for example.
Now this is the power of mathematical induction. I keep doing the same process. I project it from a higher dimension to a lower dimension and a lower dimension to a. I keep doing this. I don't want to get into the mathematical rigor of it, but the idea is that I keep projecting it into lower and lower dimensions until I get like a 2D dimension, and say that, okay, on projecting this entire high dimensional object to only 2 dimensions, it is not possible to intersect, which is equivalent to saying that it is not possible to intersect in this higher dimension. Because this idea of projection does not only exist in 3D. I can project from a 4-dimensional object to a 3-dimensional object, a 5-dimensional object to 4-dimensional object, and so on.
Yes, and I have two more questions related to this query.
Okay.
So can we convert this equality thing into the inequalities one, like all the equations which we wrote were having, equal to the right hand side.
Okay.
So can there be the situation wherein instead of equality, if it is replaced by less than or equals to number one?
Okay. And I'll come to that.
Okay.
I think Satinder, is there something that
Yeah. So I want to know that if suppose we are visualizing like x-axis is also moving and y-axis is also rotating, means x-axis is rotating and y-axis is also rotating, like coordinates are rotating, then so we'll view different lines at that point of intersections.
If x is also rotating and y is also rotating at the same time.
Means what I'm visualizing, that plane actually it is rotating somewhere. It is movable where the object has been kept. So
plane, plane is movable. Okay.
On plane, no, sir. Where the axis, what we are assumed that the axis is there, and let's visualize that the axis is movable. Means it is rotating axis.
Yeah.
So where the planes are kept, so what the line we are visualizing, intersection of the two lines, so that when we are visualizing that, we will get the different views of that. So equations will change definitely, I think so.
Okay, yeah. So that I think I should clarify myself there. I did not mean that the planes, I'm moving the planes. Okay, actually, what I'm doing is I'm moving the camera.
No, that I've understood, sir.
Okay.
There was a doubt we are getting only one equation of line. When the two planes are intersecting, we are getting only one line, and that can be viewed from different directions.
Yeah.
Line will be same. But my question is, like, suppose axes are rotating, like, so in that scenario, we'll get the different equations because line.
We'll get different equations, definitely. Yeah.
Yeah. That only I want to clarify, sir. Thanks.
So if what you mean is you are rotating the plane?
No, axis.
If you are rotating the axis in okay, so what does it mean to rotate the axis? That is the first thing I want to ask, because let's say this is your axis, okay?
Yeah, okay. Yeah,
and you are rotating this.
Not like this.
Okay.
Through certain angle, like 30 degrees.
Like this.
Is continuously moving. It is moving.
Okay. So you're moving it like this.
Yeah.
Okay. Good. So now you're asking, like, what is it?
And the two planes are kept over there, and then the line equation will definitely change. I think I will get the different lines at that scenario.
True. That is true. So what happens in this case is there is a certain offset, okay, of this happening. So the idea is that, okay, that's a very good question. Okay, there are these very complex, not very complex also, but a bit higher field, not a field, a higher object of study called quaternions, okay, which deals with exactly what you are talking about, rotating axes, okay. But before this, okay, instead of talking about quaternions, what you can always think of is I am actually taking the axis, okay, and I'm rotating it. No, so does
Yeah.
it have? So now again, I ask you the question: do you want the planes to remain the same in the same
Yeah,
state
yeah,
and then
yeah,
rotate?
yeah.
Yeah,
Play, yeah, where my planes are fixed over there at the initial position. When we have observed that the axes are stationary because
hmm.
we are not knowing that actually axes are moving.
That's
But
right.
in actual scenario, the axes are moving. So definitely my position of the plane will keep on changing.
Yeah, yeah.
So at that stage, I'm going to get the different equations of the point of intersection. What the line I'm observing, the equation definitely will change. So
Right,
the
right, right.
observer will get to know that okay, we have different lines, not one line. At that case, that was my confusion. Sir.
Yeah, yeah, yeah. That's right. That's right. Yeah. Okay, okay. So that's what you asked. Definitely,
Yes.
you will need to rename the equations. Now the question is, how will you rename the equations?
Yeah.
This is where you use matrix multiplication actually.
Okay.
So what you have is you have something called rotation vectors or rotation matrices. Okay.
Okay. Sir.
So this is used in computer graphics and so on, but the vector will look something like this. If I multiply, let's say, let's see, okay, I just want to do a sanity check. Let's say I have a point 1 1 here, and I want to uh, uh, rotate it here. Okay, I want to rotate it here, and then I multiply this 1 1. What do I multiply in order to get minus 1? Sorry, 1 minus 1. So I have 1 1 here. So all I need to do is multiply by this to get 1 minus 1. So this is an example. Okay, yeah, right. So 1 0 1 minus 1. So see, if you interpret this vector as a point in a space, okay, and this is actually not a rotation vector. A rotation vector will be slightly more complicated. You'll have to add some sine, cos, and so on. But the idea is transforming this point to this point. This vector will reflect point on x-axis. This is exactly what it does. When you multiply this 1 1, I get 1 minus 1. You can try it similarly with 1 comma minus 1 comma 1 also. Okay, so let me multiply with minus 1 comma 1. It should be working. Let's see. Okay, so if I do 1 0 0 minus 1, I should come here, which should be minus 1 comma minus 1. Is that what happens? Yes, it gives you minus 1 comma minus 1. You see, right?
Yeah, sir.
So this is the entire idea of matrix multiplication. You are modifying them so that you can. So idea is that what does this matrix do? This matrix, transformation matrix, will actually reflect everything. If there is a shape sitting here, then it will reflect it here on multiplication.
Yeah.
So similarly, you
So
have a rotation matrix that when you multiply, it will actually rotate the point across a certain axis.
okay, means it means that the line will remain same, but due to its different coordinate system, we are visualizing as a different lines, but the
Yeah.
line is same.
No, the lines. Yeah, okay. The line is same with an offset, so it can be
Of
represented by a different
different
set of
coordinates.
lines, but
Yeah.
it can be represented by a different set of lines. But those set of lines are actually just a result of multiplication with another matrix.
Okay.
Okay, you get it, no?
Okay. Yes, sir. Thanks, sir. Thanks.
Yeah. Okay. Kishore.
Yeah, I think what I thought of saying, I think we discussed just now.
Oh, okay.
So
Great.
it's just a viewpoint, not exactly the line is changing some way, but it's just a viewpoint is changing.
Okay. Oh, yeah, yeah. That's right. That's right. That's right. Yeah, Goel, coming to what you were asking, right? If you change it to um, um, if you change it to inequations, what happens? So, for example, x plus y equals 1. So, what does this look like? Okay, let's. I want it to exactly overlap with the grid of the. Okay, let's say I talk about this line. Okay, and so on. So this is nothing but x plus y equals 0. No?
Yes.
Agreed, right? So this is x plus y equals 0. What Goel is asking is, what if I consider x plus y is at least 0? Okay. Now, what is x plus y is at least 0? X plus y is at least 0 is same as this set of points, which is x plus y equals 0, x plus y equals point 0001, point 0002,
Excuse me,
and so
sir.
on. X plus y equals 1. Yeah.
So can you check the line? I think this is equation of x equal to y. So x minus y and not x plus y.
Ah, yeah. Sorry. Good. This is x equal to y, so it's x minus y. Good. Thanks for pointing out. And so on. X minus y equals 2. And so on. X minus y equals 100, and so on and so forth. This is agreed, right? This x minus y is at least 0 means that if x minus 1 is even, x minus y is even 0.00001, this object, line, plane, whatever, should capture this, should accept this. Okay, so x minus y is at least 0 is nothing but the conglomerate of x minus y equals 0, x minus 1 y equals 0.001, 0.002, and so on. Just to get a feel of it, okay, what would x minus y equals 1 look like?
So x is equal to y plus 1.
Okay.
So that would again be a line, and wherein x-axis will get crossed at the point say 1.
Okay. So if x is or rather I'll write it in terms of y equals x plus 1. So
yes.
what when x is 0, y is 1.
1.
When x is 1, y is
in fact, this is not correct, that x minus y is equal to 1, so y is equal to x plus 1. This should be something else, like say y is equal to x minus 1.
Okay. Sorry. Again a sign problem. Sorry. Y equals x minus 1, right? Is this correct?
Yes.
Okay, so x is equal to 1, then y is 0.
Yes.
X, oh sorry, x first we'll start with 0. X equals 0, then y is
minus 1. So we'll cross the y-axis at minus 1.
Minus 1.
And
Y is minus 1. And when x is equal to 1, y is
so then it will cross the y-axis at minus 1, and it will cross the x-axis at 1.
y minus 1. Yeah, you were saying okay, like this, right?
Yes. Now
Yeah.
draw the line. So yeah.
And then you draw a line. Okay, that's a very bad demonstration. Let's say this is here. Okay. Yeah.
Yes.
So the idea is that if I plot, let's say x minus y equals 2. Okay. So let's color this red. Okay. And let's say if I plot x minus y equals 2, then it will look somewhat like this. Right?
Yes.
And if I have, if I plot y equals 100, then it will be something like this.
Yes.
Right? Now, but it's not just 1, 200 and discrete points, right? There are infinite points in between, like 0.001 and so on. Right?
Yes.
So this, let's say this is the speech line, 0.0001, and that is something like very close. Okay. This
Will
is,
this result into a half plane kind of thing?
yeah.
Will this result into a half plane kind of a thing?
Yeah. Exactly. So what is the result of it? The result is that um, this entire region below this line, which describes x minus y equals 0, is captured by this. So it
Yes,
is somewhere between a plane and a line. Exactly, like a half plane.
yes.
Why is it not a plane? Because it's not extending infinitely above this. But why is it not a line? Well, it's capturing a bunch of lines, an infinite number of lines. So it's somewhere between a line and a plane. Yeah, Satinder.
Yes, yes.
Yeah, Satinder. Yeah, I'm not
Audible,
able
sir.
to.
Hello.
Oh yeah, okay.
Ah,
No.
yeah. Sir, as yeah, just now you mentioned ki it is a half plane.
Hmm.
So what I'm visualizing, if it is a like half plane,
Hmm.
then the two lines will definitely sandwich. Mean there will be no gap. So actually, I'm seeing like a parallel lines
Yeah.
from
The
one side.
parallel lines was just to
So,
explain.
but it can't be plane then, because if it is a plane, then so there will be no gap between the two lines. Because if
Yeah. Right.
lines, yeah,
So no, actually, I just wanted to show these parallel lines to
no,
to 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 make my point. Okay, about the how it will look like. But yeah, there are
uh,
infinite lines between these two lines.
from far away, if we are observing, to we can't come to know it is a gap in between. So it
Yeah,
will
I mean,
appear
in
as a
fact,
plane.
yeah, in fact, however near you look at this, it will always appear smooth because there are infinite lines between any two lines
So
within that.
it will be stacked. So it will appear from far distance. It will appear like a like logwood or like a plane, but
Yeah.
it is not so.
No. It is because these are real numbers. No.
No,
Un-
it's like in between them, the gap is there, no, sir. They are
no.
parallel, so there is a gap between
No.
them,
No.
both the
No.
lines.
No.
The
No. No.
shorter distance must be there.
No. Because Satinder, between any two real numbers, okay, can you give me two real numbers between which there is a gap? Where I cannot find a real number.
No,
No.
I can't give.
Similar with this. If you give me like this x minus y is 0.0001 and x minus y is 0.002,
Okay,
I can
got it,
always
got
find
it.
a point 0.001
So
more
it
01.
means it is okay. That was my mistake. Actually, I've taken into account x minus one equal to one, x minus two equal y equal to two. That lines
Ah,
I've considered. Actually, it is not one. It is 1.000. The next to that
yeah.
also it is there. So definitely it is a half plane. Got it, sir.
Yeah, exactly. So in this course, we are talking about real numbers only. But I agree that
Yes.
if you say instead of real numbers, if you say okay, they are not real numbers, they are natural numbers, then I agree. They are like several lines where there are gaps in between. Okay, the x
Got it.
equal this one and two. I just wanted to make a
Okay,
feel of what
I
it
got
is. Okay,
equation. Just now I've
Uh,
seen that it is greater than zero. Got it, sir. Thanks, sir.
okay,
Thanks for the clarification. Thank you.
Great, good. Yeah. So, but these are linear inequations. So they, I mean, it's slightly away from the field of linear algebra. So we won't talk about it too much. But some of you may have seen the area of linear programming. Okay. Some of you may have not, but linear programming deals with this. Okay.
Okay. And even in the case of the equalities, do we have a certificate kind of the thing that, okay, this set of the equation is going to have no solution and this is a certificate? So is there a way or is there an established method to get such a certificate that will show that this set of the equations is inconsistent?
Right. Well, so that will come in the next week. Okay.
All
So
right,
that will come in
fine.
the next week. So that is all about checking consistency and about rank and Gaussian elimination. Okay.
All
So
right.
and to answer your question, yes, there is a certificate. There is an algorithm to actually do it.
All right.
Okay.
Yeah, fine.
Great. Okay, that was the first question. Okay, I hope everything is clear. Okay, okay, let's look at the second question quickly. Which of the following are true about symmetric matrices? Okay, I'll just take a screenshot of this. Okay. Hmm. Okay, which of the following is true about symmetric matrices A n cross n and B n cross n? If not, give a counter example. So I hope you know what a symmetric matrix is.
A transpose is equal to A.
Yeah, symmetric matrix is A transpose equal to E. For example, 1, 2, 3, 4, 5, 6, 2, 3, 6. So what is this? Is A? Then what is A transpose? A transpose is just turn every column into row, row into column. So this is the first row, you turn it into column 1, 2, 3. Then you take the second row and turn it into column 2, 4, 6. Third row, turn it into the third column 3, 6, 5. Okay. If you compare these two, they are equal. So these are very special kind of matrices. Okay. These are called symmetric matrices. Another way to see it is reflecting it along the diagonal. What is the diagonal? This is the diagonal. This will remain same. 2 will be reflected here. 3 will be reflected as. On reflecting, you get the same thing. Okay. Good. Now, A plus B is always symmetric. So, which of the following is true about symmetric matrices? I'll let you guys try once.
So A plus B is fine. That will always be symmetric.
Okay.
And that can easily be proved as well. But this AB thing may not be symmetric because in the product, quite possible that during the process of taking the product, the nature might have changed altogether, and wherein rows and the
Okay.
interchanging of the rows and the column may not result into the same thing.
Okay. Okay. Good. Okay. Okay. We'll come to B. Yeah, A is correct. B is also correct. Actually, I'll give it to you right away. So good. So, but let's see why A plus B is symmetric. We need to show this. Okay. How do you show this? Well, we know. Okay. We need to show. A plus B is same as A plus B transpose. No? So, and this we know that A plus B, if you transpose it, okay, it's not going to be affected. So, so what I mean is A plus, we know A plus B transpose is A transpose plus B transpose. Okay, transpose operation distributes. Okay, because what you are doing is instead of adding and changing every rows to columns, you are changing everything to every rows to columns and then adding. It's the same process. Okay, you can prove this. It'll be just a one line proof. Okay, and A transpose plus B transpose, but A B are symmetric. Okay, so A equals A transpose, B equals B transpose. So A plus B transpose equals A transpose plus B transpose, which is equal to A plus B. Which means A plus B is symmetric. So the sum of symmetric matrices is always symmetric. The next question is interesting. Is A times B is it symmetric? And like Goel said, the answer is no. And how do you prove no in mathematics? One good way to prove it is via counter example. So at this point, I would like to ask you guys, can you come up with a counter example where A is symmetric, B is also symmetric? Of course, try to come up with a small matrix. Don't come up with huge matrices, which will be harder. But where A is symmetric, B is symmetric, but the product is not symmetric. So can you do it? Try it.
I tried a small example, but it is coming symmetric. I took the
Oh,
values of the matrices as 1, 2, 2, 1, and then 3, 4, and 4, 3. And
okay.
I took their product, but it is coming a symmetric matrix.
Okay. Okay. Yeah, Guru, you have a.
Can you hear me?
Yeah, yeah, I can hear you.
Okay. Hi, sir. I tried taking 1001,
Okay.
1.
Okay, let's try 1001
Yeah,
and
0110.
0110. Okay, let's try that. Are they symmetric? Clearly, it
Just
is.
0110. It is symmetric at that.
Yeah, yeah. They are both clearly symmetric. Now,
Yeah.
you multiply them, you get 1 times 0 and 0 times 1, which is 0. Then you try this part will be 1 times 1, 0 times 0,
And 0 times 0.
0,
That's
0.
fine.
This will be 1, and this will be. Oh, no, this
0.
is symmetric, right?
Yeah.
Oh, this is still symmetric. Okay. Okay, probably we need to move to dimension 3 then. I think come up with a 3 cross 3 matrix then. Because 2 cross 2, I think it will be difficult to avoid the symmetricity property. I think, probably. And also, Guru,
Yes, sir.
try to avoid identity matrix.
Okay.
Because see this because matrix this second matrix is already symmetric, so when you multiply it you'll always get the second matrix with that, right?
Okay.
So this will obviously be symmetric,
Okay.
right? I times that b will be equal to b. Yeah.
Possibly,
Yeah, sure.
I think one matrix A has 1331,
A
row
is
first,
1331,
and matrix B has 2662. The product,
2662.
yeah,
Okay, let's see. The product is 2 plus 6 is 18, 20.
yeah,
6,
2012 and 1220.
12. But that's again symmetric, no? If it's 12, 20. 6 is it?
Okay, sorry. I think we are trying to not symmetric, right?
Not symmetric, yeah. Okay. I'll give you just like, guys, 30 seconds, then maybe I'll also attempt. I also don't know a counter example, so I'll be Also in the same boat, probably. Let's see. So try 3 cross 3. Maybe that'll be better. Yes, Satinder.
Sir, can we take this one like 3
Huh? Okay.
row
Wait.
wise? I'm telling
Okay. 3.
row wise. 2 iota.
3. Then
2 iota.
2. What? Why? 2 I ka?
Iota.
Imaginary value I. So
Oh,
Yes.
okay. That okay.
He's
2
taking a
I's.
complex.
Okay. Very creative. Okay.
not in this way, but then probably he's asking 3 is the first element and 2
2 iota in the second.
Oh. Okay. So you mean like this?
Yes, sir. It is because you have not said it, only we have to take real values. So then next row will be 2 iota
Okay.
4.
4.
So
Okay.
this is symmetric.
So I guess when you multiply the
Next
i's,
number. Next matrix will be iota
Okay.
2 iota.
Okay.
Then down is 2 iota
Okay.
0.
Okay.
So I think we'll not get this.
Okay. So this will be 3i.
But the second matrix is not symmetric one.
Yes.
I 2
Yeah,
I
second
2 I
matrix
0
Second matrix is
is not symmetric. So we have to
it is
take
symmetric, no?
symmetric matrix.
Oh no, it's symmetric. It's symmetric.
It is symmetric. Yeah.
Yeah, it is.
Second matrix is not symmetric. So therefore, I mean, because we have to take 2 matrices A and B and which are symmetric. So like in the example which Satinder gave, the first matrix is a symmetric. I mean, neither first nor 2. Both the matrices are not symmetric.
No, they are symmetric.
So they are symmetric. Both are symmetric. No.
First row,
You can take the first row 3 and then take 2i below it, and then if you take 2i and 4 below it, 4 remains in the same place as it was in the original.
and what about the second matrix here? I 2i and then 2i 0.
Yeah, it is symmetric. No, because see, when you transpose it, you get I 2i, and the second row is 2i 0.
Oh yes.
Yeah. So it is symmetric. Both are symmetric.
Yes.
Okay. Let's try it. 3i plus 4i square, which is minus 4. Okay. And this one is 3 to the 6i minus 0. Okay. Then 2i square is minus 2. And 4 to the 8i. Okay. And the final one. Okay, this is already non-symmetric, yeah? 4i. Okay, yeah, good. Okay, this is a good example. I have a very creative example also. Yeah.
So it will be not, it will be not symmetric.
Yeah, this is not symmetric. Good. And
Sir, I have one more example.
Yeah. Good. Can you tell me?
First matrix is 1, 2, 3,
1, 2, 3,
2, 4, 5,
2, 4, 5,
3, 5, 6.
3, 5, 6. Okay.
And second matrix is 7, 8, 9,
7, 8, 9,
8, 10, 11,
8, 10, 11,
9, 11, 12.
9, 11, 12.
I got the product as 50, 61, 67,
Okay. 67,
91, 111,
111,
122,
122,
115,
115,
140, 154.
140, 154. Okay. This product will take time to verify. I think I'll verify it. It's an online tool.
Okay.
Hiranmoy, you have one question? Yeah, Hiranmoy, you have raised a hand. Okay. Hiranmoy? If you are speaking, I cannot hear you. So what are the points? Um,
1, 2, 3.
1, 2,
3.
3,
2, 4, 5.
2, 4, 5,
3, 5, 6.
3, 5, 6,
And coming to the second matrix, 7, 8, 9.
7, 8, 9,
8, 10, 11.
8, 10,
10, 11.
11,
9, 11, 12.
9, 11,
12.
12. Okay, wait. Calculate. This is what you got? Okay. Good.
Yes. Yeah, it is the same.
Good. Okay, great. Yes. So this is an example of a real matrix. But this is non-symmetric. Nice. Good examples. Yeah. Okay. So Hiranmoy? Okay, count. Okay, great. So this is an example. So now the question comes. Okay, but notice that it's not that AB is always non-symmetric. Also, when you guys tried, so many matrices were actually coming as symmetric, right? So question is, when is it so that AB is always symmetric? So that is the next question, and that is the next question. That is the question we ask, and that is exactly the next question I've written here, which is question number 3. Okay. Delete. Okay, great. This is exactly the next question. Okay, so the question is, show that A and B are symmetric matrices. Okay, if A and B are symmetric matrices, their product AB is symmetric if and only if AB is equal to B. Yeah, Satyendra, you have a question?
Sir, just I want to know like A transpose we are doing, like calculation to for calculation purpose we are doing, but I'm not getting the idea of like what is geometrical meaning of A transpose. Like if I'm visualizing as a vectors or points in a 2-dimension or 3-dimension. So when we are doing a transpose, so actually what we are doing, this I want to know, sir.
Okay. So let's visualize that with points, okay? Or I'll come to it just after this question. Is that fine, Satyendra?
Okay, sir. Okay. Thank you, sir.
Great. Okay, just to remind myself, I'll write this transpose here because I have a very bad memory. Okay. Anyway, yeah. So show that if A and B are symmetric matrices, the product is symmetric if and only if. It's not even if. If and only if means both directions. Okay. If and only if AB equals BA. What does if and only if mean? It means product is symmetric if AB equals BA and AB equals BA if product is symmetric. So we need to show both directions. Okay. So let's see. First, this direction. AB is symmetric. Then AB equals BA. Okay. So let's say AB is symmetric. Suppose AB is symmetric. Okay. Then what does it mean? AB equals AB whole transpose. No? Then what does it mean? then what is AB whole transpose? You saw in the lecture, which is nothing but B transpose times A transpose, right?
Yes.
And so then what do you have? AB, okay, I'll write it below, equals B transpose times A transpose. But what do you have? A and B are symmetric matrices. So since AB are symmetric matrices, since AB are symmetric, A equals A transpose, B equals B transpose. No? So I can simply rewrite this B transpose as B and rewrite this A transpose as A. So therefore AB equals B. So the first direction is done. AB is symmetric means AB equals B. No? So the next direction, AB equals BA, then AB equals BA, then AB is symmetric. Okay, can you prove this? I'll give you a minute. It's very similar to the previous one. So
Yeah. So let us take the transpose of both the sides then. If
Okay.
AB is equal to BA,
okay,
then AB transpose is equal to BA transpose.
AB transpose equals BA transpose.
Yes. And why so? Because I mean it's okay. Can we do this thing? Yeah. And the right hand side then can be written as A transpose B transpose.
The right side can be written as okay.
Yeah.
So you are doing A transpose B transpose.
B transpose.
Okay.
But then this equals to what? AB? Because
This
A
is equal
transpose
to
is equal to
AB because AB are symmetric. Right?
Yes, so proved that AB is symmetric, isn't it? That the AB transpose.
Yeah, I mean because that's the original assumption. No? AB are symmetric.
So you can,
Oh,
so you can
okay.
continue that proof.
Yeah, sorry, Amlan, I could not hear you. Sorry, can you repeat?
I'm saying you can continue that proof. A into B transpose equal to B into A transpose. You can continue that proof, and I think you'll get the answer.
Okay, wait. What did you say? A?
So solve for the left hand side too. Total transpose. Second equation, sir, where you have written that AB equal to BA. Try to solve for the left hand side too.
Try to solve for the yeah. Okay, yeah. You mean this side instead of this side?
Yeah. Expand it. So just expand that left hand side. I think.
But why do we need to expand?
I think you can see the proof if you just you can already see the proof even if you don't.
So we don't need to expand. No, because if I mean not expanding itself is giving me that AB is actually symmetric. No, which we want to prove.
I was actually going the reverse of the proof. That's why.
Okay. Great. Okay. Yeah, good. That is the way to prove this. So what does it do? It gives us a characterization that if I want to check if the product is symmetric, it is enough to check if the two matrices are symmetric, and this is followed. This is what is called commutativity. Okay. For example, numbers satisfy commutative multiplication. For example, 5 into 7 is same as 7 into 5. 6 into 20 is same as 20 into 6. But in matrices, it's not the same. But if it is same, then it means that if the multiplications are same, it means that the and the two matrices are symmetric, it means that the product is symmetric. Okay, so there's a nice characterization. Great. So okay, yeah, transpose. So okay, who was on? Satinder, I think you asked this. Huh?
Yes, sir. Yes, sir.
Okay, great. So let's try to see it with an example. Okay. So let's take a simple matrix like 1, 2, 3, 4. Okay, and see what its effect is. For example, okay, you want to see it in terms of system of equations. So 1, 2, 3, 4, x1, x2 equals, let's say 1, 2, 3, 4. So x2 equals 2, 4. Is this consistent? I'm not sure. Okay, let's take the popular one only. 1, 2, 2, 1. This is 3. This is 3. This is 3. Okay, yeah. So its solution is 1, 1. Those things we already know, and it is consistent also. And if you want to represent these lines, what do they look like? Okay, so x1 plus 2x2 equals 3. What does this look like? When x1 is 0, x2 is 3 by 2. That's an ugly one. Okay.
It will be intersecting lines. It will be intersecting lines.
It will be intersecting. That is true. But we want to see the consequence of transposing it, no?
Yeah, sir. I want to get the idea of like what actually transpose is doing actually.
That's right.
Then
That's right. See, what transpose actually does is it is a rudimentary form of rotation. Okay, because I wanted to show it visually, but the plots I do may take time. Okay, see what happens when you transpose. Okay, so this is the equation, no, and here you have transpose. Oh, sorry, and here you do this. No, okay, and so this is the first equation, and this set of equation represents x1 plus 2x2, 2x1 plus x2 equals 3. Now, if I do the transpose, okay, if I do the transpose, then what do I have? 1, 2. Oh God, okay, this is symmetric. Bad example. Okay, 1, 2. Let's say 2, 3, 1. Is this symmetric? This is not symmetric, no?
Not symmetric.
Okay, great. So when I transpose this, I get 3 here, I get 2 here, right? 1, 2 becomes 1, 2 here, 3, 1 plus 3, 1. Yeah. So I do extra.
There would be a change in the equations as well. You wrote x1 plus 2x2 is equal to 3, and then 3x1 plus x2
yeah,
is equal to
3x1 plus x2 equals 3. Now, if I do this, write it in terms of equation, I get x1 plus 3x2 equals 3. And 2x1 plus x2 equals 3. Okay, is that right?
yes, sir. We get both the equations.
I give what?
Before the transpose one, we have got already that x1 plus 2x2 equal to 3.
That's right.
X1 plus, and second one is the transpose of that. We have got both the equations.
That's right. Yeah. So outright we do not see any relationship. That is true. Yeah, it's not even that the accesses are actually interchanged, because
Sir, what I'm visualizing, like if you'll take only one coordinate, like like if I'm going to take 2 x 1 matrix, suppose 1 2.
Hmm.
So 1 2, if I'm doing the transpose, it comes out to be row matrix 1 2.
That's right.
So it means that the transpose actually the coordinate system, like if you're taking 1 unit from the x-axis and 2 units from the y-axis, means that now the system of the equation will be changed in the new transformation. I think so. The
That, that's
transpose idea is that.
that,
Ki,
that's right. I mean, if you are talking about vectors, okay.
No, I mean, I'm just sir, like actually there is a lot of confusion. Like, na, ki matrix itself only is a
No,
that
no,
part, na,
no.
coordinate.
See, what you are talking about is if I have 1 2, this is a vector. No, it is a one
No,
time. It has
1 2 coordinate system 1 comma 2, 1
yeah.
comma 2. If any point you take.
I know. See, this is the same as 1 comma 2, right? Because
Okay.
when you multiply, I mean, or this whatever, it's this, right? So 1 comma 2 is what you are talking about is a coordinate 1 comma 2. And these two are equivalent. So vectors actually represent coordinates in space. Okay, these are one-dimensional matrices.
No. This I'm only means if I'm taking as column matrix 1 2. So if it represents the point,
right?
So what I think, sir, ki maybe the transpose represents the transformation. What we are doing for the next, we are visualizing in the next coordinate system, in which the x-axis will be 1 unit and now y-axis will be 2 units. I think basic idea of the transpose may be this.
So what you are saying, you are interchanging the x and y values, right? That's what you are trying to say.
Yeah. Transpose that only we are doing.
Yeah, I mean, see, I was
Excuse me, sir,
imagining.
can you hear me?
Yeah, Amlan.
So I just googled the question. What's
Okay.
the geometrical significance of a transpose? It says that a transpose of a matrix can be geometrically interpreted as a reflection across the line y equal to x in 2D space, effectively switching the rows and columns of the matrix.
Okay.
So it's saying it is a reflection. It's a reflection about the line y equal to x.
Yes.
So
This
the
makes
y equals x line is this. Oh, sorry. Y equals
Okay, got
x
it.
line is this.
X y will be changed into y-x
X.
coordinates.
No. So
Okay,
that's
reflection of this point along other one.
yeah,
I think.
exactly. This will be a reflection along this.
Got it. So that will be in 2D dimension. So in 3D means it must be reflection along a plane. I think so. If you are taking
if you are taking a plane,
3D, so it must be reflection along a plane then.
it should be a reflection across a plane. That's right.
So this means that
what is yeah.
What I'm concluding that if the matrix is symmetric for like system of the equation, for the system of the equation, the A matrix is symmetric. It means that we are going to change the reflection, though line, so line is not going to affect. Both the lines will be same.
That's right.
Yeah. So this is the main. I think that is the part.
Yeah. That's a very good point that you brought in. That's actually it's very interesting. I'll look into it because there's still like several questions you may ask, like when you say reflector along the plane. I mean, this was x equals y, right? The line x equals y. Now, if you want to talk about higher dimension, then what is the reflection across, right?
Yes. So actually, I don't have the idea above 3 dimension. Like
I mean, okay, no, until 3 dimension is also. I mean, no one has idea above 3. No one can visualize above 3 dimensions. But
actually, just in books it is written 4D, 5D. But for me, it is beyond of understanding level because I can't even think of that what they are talking about, like 4 dimension, 5 dimension. So actually, 2D and 3D is only tough to visualize and to understand. Like bookish things to learn, so it's easy. But true education or true knowledge will come by interacting only. That actually what we are doing. Once we'll understand, then there is a real interest of studying, sir. What I feel. And actually, we people, actually, we are not a toppers, but we want to think. So what our education system is there, so they don't provide us such a platform to study, to interact. And what I found that this NPTL or SWAM, this government has given the initial that we are in the remote village area and we are getting the opportunity to interact and to understand the subjects. Actually, our aim is not to get the job.
Right.
I want to understand maths. I want to like it is a music, like it is a movie for me. Instead of watching 3 hours movie, I can interact 5 hours maths,
That's
and
right.
that will give me a true essence of this. So that is a true education, but no one is interested in this part.
That's right.
In the education system, totally, it is not just they are taking the toppers. So it is not only the top, because they can learn and they can write the same thing. It doesn't claim that they know everything. So that only, sir.
Yeah,
Thank you, sir.
that is true, Satinder. I mean, it's good that you are, I mean, having a genuine appreciation for education, mathematics, and
Yes, sir.
yeah. I mean, keep this up. Good thoughts. Very positive
Thank you,
thoughts.
sir.
Yeah, and yeah, you brought in a good question also. I actually want to look into this in detail. I'll come back in the next week and talk about this. Maybe that's a nice thing. Or maybe we can also do something like if you look into it. Okay, I'll also look into it. But if you look into it, then maybe you can talk about it in the next session. We can have it like a nice discussion between everyone, right? So, and it's not only to you, but the other guys also in the group, right? So I think it'll benefit
Excuse me, sir.
everyone. Yeah, Amlan.
Excuse me, sir.
Yeah.
Sir, the next session will be on the same day, and you'll be taking it, right?
Yeah. So actually, there are two TAs for this. Okay. Yeah, for this course, there's me and I'm sorry, I forgot his name. But okay, let me try to recall. Yeah, I'm sorry for
Probably Rupesh.
but yeah,
Probably Rupesh.
Rupesh. No, yeah, okay. So Rupesh and I will be doing this, but Rupesh's are on Tuesday. Sorry, Friday, and mine are on Tuesdays. Okay, but the content, I mean, the matter discussed within that will be the same. Whatever the week's content is will be discussed. The questions may be different. Okay, and the flavor may be different, but it's the same content. It's up to you which one you want to attend. My sessions will be on Tuesdays every week. Okay, 6 p.m. Just give me one moment. I'll charge my laptop. Okay? Yeah. Okay. Great. Yeah. Okay. So my sessions are on Tuesdays. Okay. So the next session I'll be conducting will be on Tuesday. Okay. That's clear, right, Amlan?
Yeah. Thank you, sir.
Okay. Great. Okay. Any other questions? Yeah, Guru.
My doubt was, sir, is there any direction in which we should train our mind so that we can keep our mind open to understand linear algebra?
Okay. See, Guru, it's different for different people. See, so mathematics is something that to some they find beauty in the abstractness of mathematics, and some they find the beauty in the practicality of mathematics. So these are two very different areas. Some people you need to motivate them theoretically. Okay, you need to say that. And what is that? I mean, pure mathematics is just mathematics to create more mathematics. That's what mathematicians do, right? But there is also something called applied mathematics, which is that is for people who want to use that mathematics somewhere. If I say that, okay, transpose is these are the properties of transpose, these are the properties of symmetric, and so on. Someone from an applied mathematics interest may not appreciate it, but they'll say something like, "What's the point of this?" Okay. but until you show them an application of it. So first you should determine like which category do you fall into, because the first category will appreciate the inherent beauty of it, on looking at the theorems, and you say that, oh, that's very interesting, because that's very surprising in its own right. And the other kind will say that, oh, this looks very useful, maybe I can apply it somewhere. And then they look at the application and then they say that, oh, you can use it in such and such places. First you need to identify what appeals to you. Ask yourself the question, are you more of a mathematician? I mean, of course, both are skills that can be learned. There's no such inherent thing, but you should think yourself that, am I more of a mathematician or more of an engineer? Okay. And therefore, you should pursue in that direction. If you are more of a mathematician, then you should look at courses and textbooks that are talking about pure mathematics. It's just mathematics to do more mathematics. There are some people who enjoy that. Else, there are particularly materials which talk about applying linear algebra. It's not like they don't teach linear algebra in depth. They do teach linear algebra in depth, but then, show applications. So that from a more, say, an engineering perspective. Okay. For example, linear algebra is used all over the place. I mean, it's used in my field. It's used in, say, electrical engineering. It's used in data science. It's used all over the place. So if you find motivation there, then you can look into linear algebra on these places. But there are these basic linear algebra courses which are not too much in depth. I should say you should look into it regardless of that. It will benefit you regardless of which direction you get into. Does that answer your question, Guru, or did you mean something?
It does.
Oh,
it does.
Okay, great.
My main motivation to join this course was I used to sit and do calculations for my project work during my engineering time.
Okay.
So every time I used to come across a vector, like a resultant force going in a different direction.
Okay.
So,
yeah.
Like that, I used to come across this concept everywhere, but I never got to learn it in depth. That's why I came here.
Okay.
Thank you for answering that.
Oh, that's great. Yeah, I think this then this course is meant for you probably because I mean I think it's linear algebra but with a a really different and fun perspective. Yeah. Good. Yeah, Satinder, you were raising your hand, I saw.
Yeah, sir. That only I was saying ki, like actually people want to study for maths or physics or chemistry or engineering for a job purpose, not for the knowledge. Because sir, what I feel, once you'll get the knowledge, then the world will be after you. They want to know that how you did it. So because once you get a thing that okay, I have thought this in a different way and this was my idea. So people will, when they will realize, okay, this person is able to think and it's so easy, and why I'm not able to see this picture? Because maths is not all about just solving a question. What I feel, okay, let your question is wrong, doesn't matter. You are awarded for the thinking, like what the idea you have got while generating that solution.
That's right.
So maybe you failed, but doesn't matter. Because when we interact in a group like 10, 15 or 20 people, those who enjoy the math, so really we get the that time, okay, that person is thinking in that way. So next time we are also get the different directions, because one person can't think in 50 different directions.
That's right.
So but today's world is like, okay, if I'll study this, I'll get that job, because no one wants to study actually. This atmosphere is there.
There are, I mean, you are right. I mean, in today's world, there are very few people who study because they like studying. Maybe they do, but the final purpose would be like for a job or something like that. For example, a large percentage of most people preparing for entrance exams, they are doing it for the entrance exam,
like for the packages. They will get the high package of that one.
Yeah, for the high packages. That's
like sir, what I feel ki, like the basic what we has been taught in the school from the beginning. Like suppose that class 5th or 6th student has to do a prime factorization. The teachers take it so easy. They say, oh, okay, go and do the prime factorization of 25, 35, something like this. So when I was in class 5th or 6th, I realized it is very tough job. And when I matured enough, then I realized actually it is the unsolvable problem. You can't factorize a number because my thinking is not like 25, 35. If like your mobile number is given, how did I factorize if it is a prime number? So later on we realized so because once you, and this education system is very good, like what the courses has been made, that has been made by the experts, the subject experts. But what the trending is there, no one wants to enjoy that maths. Everyone wants to know that this question will come in the exam. That is very important. This should I study? Because okay, let it be. You can't go with all the topics. One topic, once you are understanding, there is a lot of depth because 2000 years has been passed for one topic. It's not so easy. And linear algebra, so it is the application, I think, of all the things, whether it is in space, technology, or maybe what we are thinking of the black holes, or maybe of this. I think linear algebra has a lot of scope. But one thing is, if the basic is clear, then only a mathematician can think of that what is going on. Actually, patterns.
That's right. Yeah. That is true. Yeah. Good. I think you'll do well with this attitude. I think keep it close to you, and don't lose this drive.
Yeah.
Yes,
sir. Thank you, sir.
Because it's these kind of attitude that actually make the major changes in the world, right?
Yes, sir. Thank you, sir.
Yeah. Good, Satendra. Okay. And yeah, like I said before, if you come up with, if you see somewhere some interesting things that is related to the course, then maybe in the next coming problem sessions, you can share it. Okay. Anyone can share it during these discussions. Okay. Okay. Maybe we can do 2 questions. I will skip the 5th question. Okay. So I'll look at 4. Okay, so this is the question. So this is another interesting question. It says that every square matrix, okay, can be written as A equals half A plus A transpose plus half A minus A transpose. Okay, and show that half A plus A transpose is symmetric and half A minus A transpose is cube symmetric. Okay, and so okay, let's handle the first part. Okay, can you prove this? Can you say why this is true? Every square matrix A can be written in this form. Then we'll come to the next part. Any A can be written as A. Okay, this is square. Let's say n cross n. Okay, half of A plus A transpose plus half of A minus A transpose. Okay, I mean the answer is it's quite straightforward. Okay, so yeah, well,
no, I mean we cannot use the normal algebra here. So I was thinking that why would it won't be true for non-square matrices then?
Oh, why would it not be true for non-square matrices? Good question. Any idea?
So because here So in the case of the non-square matrix, probably the dimensions of the A transpose won't be same as the dimensions of A.
Good.
Therefore, their addition.
Yeah. Good. So let's say this is your A. Then what is A transpose? It will 1, 2, 1, 3, 5, 2, 4, 6. You can't add this. Not possible. Okay, so it needs to be square.
Right, and then we can go for algebraically. I mean,
that's right.
Then the values.
So then the idea is just that you multiply this, because scalar multiplication is distributive. Okay, half of A transpose plus half of A minus half of A transpose. Also, you saw in the lectures that matrix addition is commutative, okay, and associative also. Commutative means that you can shift the position. I mean, you can swap the position. A plus B equals B plus A. Okay, so let us swap them. So this is half A, and I'll swap these two. Okay, plus half A plus half A transpose minus half A transpose. Okay, and you can cancel this out, and when you add this, you get A. Okay, so okay, now this is clear. Any A n cross m can be written as the sum of half of A plus A transpose plus half of A minus A transpose. Now, the question asked is, show that half of A plus A transpose, this part, and half of this remaining part, show that this part is symmetric and this part is non-symmetric. Can you argue why?
So, what's the meaning of the term skew symmetric? This is a new term for me.
Okay, one moment. Symmetric. So what is skew symmetric? Skew symmetric means A equals minus A transpose. Okay.
What would it mean that I change the rows to the columns to the rows, and then what this minus indicates here? Minus values.
Yeah. So all the elements are multiplied by minus 1, in other words.
Okay.
Yeah, Kishore?
Yeah, it satisfies. The first part is symmetric, and second part is skew symmetric.
Yeah. Okay. Why? So how do you say that the first part is symmetric?
Because A transpose is the one. A is equal to A transpose.
A equals A transpose.
Because the matrix what I have taken for A is 1724.
A is 1724. Which one are you saying? You are saying this one?
Right. The
Oh,
example itself I have taken that for simplicity.
Oh, okay. No. Oh,
And,
okay.
So when I do off of A plus A transpose, what I'm getting is off of 2998.
Oh, okay. Yeah. Okay. So yeah, this you'll just get okay, half of something like 2998. Yeah. And then
So
half.
multiply it comes to A.
And this is symmetric, and therefore this is symmetric. Yeah.
Right.
So what you are saying is you'll use the same argument here, no?
Sorry.
No, I'm asking about this part. Show that half of A plus A transpose is symmetric always.
Right. The first part.
Hello.
So yeah.
So, like, if it is not a square matrix, so sum will be not possible only.
If it is not square, yeah, that's not possible. But the question is saying square matrix.
Okay.
Yeah,
So then it is always.
Yeah. That's what Goel was pointing out. Why is this necessarily a square matrix? Otherwise, sum is not possible. That's right. So yeah. So A plus A transpose is symmetric. Why? Because A plus A transpose is symmetric. Okay, A plus A transpose is symmetric. Yeah, one way to demonstrate that would be something like A, B, C, D plus transpose of this, that is A, B, C, D. Okay. Now, what do you get? You get 2A B plus C, C plus A. Oh wait, what am I doing? Yeah, C plus B, B plus C, and D plus C, 2D. Why is this happening? Because when you transpose, the diagonal remains the same. Okay, when you transpose, this guy always remains the same. And what happens to the remaining people? They are reflected right across the diagonal. So B is taking C's place, C is taking B's place. And when you add them, what is getting added? B is getting added to C. But B and C were swapped with each other, right? It's always the reflection partner that is getting swapped with each other. For example, I can take a bigger matrix and demonstrate that A, B, C, D, E, F, G, H, I. Okay, and plus its transpose, which is A, B, C, D, E, F, G, H, I. So what is so if you look at the diagonals are same. So when you transpose, when you add them, you get this part as same. I mean, so when you add them, you get 2A, 2E, 2I, A plus A, E plus E, I plus I. The remaining parts, B gets added to D. Okay, B gets added to D. But what do you notice? This swapping that happens was anyway with the partner of D. Right? So if you look at this area, if you want to find, then this B gets added to this B. So B plus B. And similarly, C and G will be added, G and C. C will be added to G, be added to G. Of course, this is not a formal proof. Okay, you can try it later on, but I'm just giving an intuition. Okay, you can even prove this using the general idea of transpose. I'll tell you anyway. So what you are doing is at any position ij, okay, you are adding aij. The transpose is aij. What happens when you transpose aij? J gets swapped with I gets swapped with J. So that aij plus aji, which is nothing but 2aj. Okay. And oh, sorry, what am I saying? Not 2aj. Sorry, what am I saying? So this is what happens every time for any ij, position ij. So now this is exactly what is happening here. Any ij pair is a where the sums are same. Okay, aij and aij and aji are actually the reflection partners. Okay, but that is the intuition. And now because A plus A transpose, we saw that it is symmetric. Then even on multiplying it with half, this is symmetric. Actually, this was also told in the lectures that this is symmetric, right? Now, next part is that half of A minus AT is Q symmetric. Same argument. It's just that you are doing A plus minus of AT. Okay. Now, since there is a minus, okay, and what is the definition of skew symmetric? A equals A minus A transpose. You have the same sequence of arguments that shows that this part is skew symmetric, and therefore multiplying with half, this is also skew symmetric. So you have this, and okay, this is simple. You just plug in the value. The second part is simple. You just plug in the values of A equals 1724 and get the symmetric and few symmetric parts. Okay. But what is the essence of this question? Essentially, this question says that any matrix can be written as a sum of a symmetric matrix and a skew symmetric matrix. Okay, so this can be stated as a theorem also. I just want to quickly, before this session ends, okay, I just want to quickly do this question. Okay, just to give a quick application. Okay, I'll give you 1 minute to think about it. Okay, a factory produces 3 paint colors by mixing amounts of 3 base colors, red, blue, and yellow. As you know, any pigment can be created by mixing suitable amounts of red, suitable amounts of blue, yellow, and so on. For example, purple is a mixture of red and blue, and maybe orange is something like 1 red and 2 parts yellow, and so on. Okay, it's up to me how much red, how much yellow I want, and get different pigments. But this factory only specializes in 3 colors. Okay, that is paint color 1, which uses 2 units of red, 1 unit of blue, and 0 units of yellow per liter. Paint color 2 uses 0 units of red, 3 units of blue, 1 unit of yellow per liter. Color 3 uses 1 unit of red, 0 unit of blue, and 4 units of yellow per liter. What we want to produce is 10 liters of color 1, 5 liters of color 2, 8 liters of color 3. Question says, how many units of each base color are needed in total?
So we can write the equations like, say, 2x1 plus x2 is equal to 10, and then 3x2 plus x3 is equal to 2, and then x1 plus 4x3 is equal to 3.
Okay, what does x1, x2, x3 represent here?
So that I was thinking.
Okay, yeah.
Sir.
Good. Good, yeah.
His solution is right, but can we take all the coefficients of those x1, x2s as a matrix?
Yeah. We can. That's what I wanted to talk about. You can interpret it in 2 ways. One is as a system of equations, and another as a coefficient matrix, right?
So this x1, x2, x3 are colors. Can we say that?
Colors, for example, x1 can be.
When we say two units of red color, that is 2x1.
So
And
x1
1 unit of blue, that makes x2, and at the total per liter it's 2x1 plus 1x2 equal to 1 liter of paint color 1.
So x1, what you mean to say is x1, x2 cannot hold values. X1 means red.
When you are saying mathematically, when you are saying.
Yeah. So what you mean that these are not variables. X1 means red, x2 means blue, x3 means yellow.
Right.
But if we solve this equation,
we can't put into
values,
linear equations. Linear equations, you are saying.
Yeah, but if we solve these equations, you will get some values for x1, x2, x3, right?
Right.
So what would that mean?
So
I mean, that's you're close, but not close enough. Yeah.
yeah, so clearly this x1 is not the number of the units of the red color because we have been given 2 units. But
x1 is what?
X1 clearly is not the number of the units of the red color because 2 is the number of the units. 2 units of the red color is already given. So what this x1 here is then the share of the red thing in making 10 liters of the paint of the color 1. How much share is occupied? So this x1 is here refers to the share of the red color, and yes. So the share of red And so x1 and x2 and x3 would refer to the share of red, blue, and yellow.
Okay. I think
So
I think this unit and liters are actually making a lot of confusion, right?
yes.
So I'll okay. Yeah, I could see the confusion. Just imagine that unit and liter are the same. Okay, now think about this. Let's say unit liter are the same. Okay. Wait, or should they be same? That's what I'm thinking. Um, oh, they should not be the same, no? Yeah, it's actually no. Okay, no.
So I mean something which is synonym to the cost kind of a thing. Say cost of a red, and so I require 2 unit of red. So the total cost would become 2 of x1 kind of a thing, and that will result into the 10. But then this is the liter. So this would result into. But I'm thinking on the lines we used to formulate the problems for the linear programs. So they're always the objective is to optimize the cost. But here,
Okay. Yeah, I think there's a mistake in the question. Is there a mistake in the question? 2 units of red.
Sir, is it similar to that system of?
Can you please scroll up a bit?
Yeah.
Can you please scroll up a bit?
Similar to that system of
Question is not
equations where we
yeah.
Okay. Yeah.
have
Scroll.
a system like 2r plus 1b is equal to 10.
That's
3b plus 1y is equal to 5.
that's the idea.
1
Yeah, good.
r plus 4y is equal to 8.
Yeah. I'm just thinking of this the unit and the liter confusion. Is that correct?
Okay.
Is it how many units at the end, or is it how many liters? That is.
Hello.
Yes, Satinder.
Hello. So what I think maybe the paint color 1 is of I think 1 unit. 1 unit of paint color forms by 2 unit of red and 1 unit of blue and 0 units of I think whatever the third color is there, yellow I think. So maybe the question is talking about 1 unit of color 1, 1 unit of color 2 means liter only. Second 1 unit of the second color requires this, and 1 unit of the third color requires this. Now we have to frame that now 10 units of the color 1 and 5 units of the color 2 and 8 units of color 3 requires what proportions of red, blue and yellow. I think this may be the question.
Yeah, I mean, what you are saying is replace this with unit, no?
No, I don't
I'm not saying.
unit as some kind of a proportion.
No, I'm saying the question may be referring as color one is for 1 liter only. For 1 liter, we for 1 liter of color 1 we require 2 unit of red, 1 unit of blue, and
That's
one
right.
0 unit of yellow. This I think this means whatever the
It is like
information is given,
mixing in
it is
parts,
1 unit of color wise. It is 1 liter of color wise. Hello.
Let's see. Just give me one moment. Yeah. Sorry.
So I think the question is fine. What it says is that we need some units of red, some units of blue, and some units of yellow per liter, means to produce per liter of paint color 1.
That's right.
So
That's right.
it's basically saying that we need such amount of red, such amount of blue, and such amount of yellow to produce 1 liter of this color.
That's right.
This is paint color 1. So we can frame this in equations exactly like Guru told. 2 times into red and 1 times into blue and 0 times into yellow gives us 1 liter of this paint color 1. So what would 10 liters of paint color 1 require in each of those units?
Yeah, but see the slight the only difference, I mean, the slight problem I see with this is, see, if I have 2 R, okay, plus 1 blue plus 0 yellow equals 10, right? This is the kind of framing that we want to do, right? Is that not so?
Yes.
No, sir.
Yes. This is correct, sir.
This is
This is
correct.
correct.
And
Yes,
then
sir.
and then you want to say that 0 R 3B plus 1Y is 5, and 1R plus 0B plus 4Y equals 8. See, I don't question the approach. The approach should be this only. What I question is what they are asking, the units of each base color. Okay. Now, what we are seeing here is I want 10 liters, and for each liter, I want at least R units of
To be
red. Yeah.
yeah, correct, sir.
Right. R units of red and B units of blue. Now let's say what would be something like when R equals 3 and B equals 4, it is satisfied, right? 2R plus 2 right, 6 plus 4 equals 10. This is satisfied, right? So I'm just not looking at this. I'm not looking at this for a moment. I'm just giving a separate value. So what this would mean is 3 units of red and 1 unit of blue. Not 1 unit of blue, 4 units of blue will give me 10 liters of paint color 1. No? That's right, right?
Yeah.
Now the problem that I'm encountering is how does it translate to liters? Because per liter,
I understood.
right? You get what I'm saying?
Yeah.
Per liter, I want 2 units of red and 1 unit of blue. Let's
Or we can do it like this, no, sir.
So, one moment. Okay. I want 2 units of red and 1 unit of blue. No, per liter. I have 3 units of red and 4 units of blue. Okay. I mean, that is solving my equation here, which means for 10 liters of paint, it is enough to come up with 3 units of red and 4 units of blue. But first, so I want 10 such liters. Okay, there are these 10 circles, but I just have 3 units of red, so I'll fill this up with 3 units of red. Then I get another unit of red, and I'm done. So in order to get the actual unit, I need to multiply it with 2 or something like that. You get what I mean? You see the problem in the question, no? That's why I'm saying that the question needs a modification in the way that it's stating. I get it that the motivation, I mean, the way to solve it is like this only. Yeah, Amlan, you were raising your hand.
Oh no, I was raising my hand previously. Sorry, I haven't taken it down.
Oh, okay, but you understand the problem now.
Yeah, I got it. I thought initially that it could be just solved as a equation. Like initially you can solve each equation separately and then just add the number of reds, blues, and yellows to get the total. But then I see the problem now that after solving you just got 3 red. But how can 3 red cover for 10 liters?
Yeah, exactly. Okay, how can 3 red cover for 10 liters? So it's not the 3 red units, but it is actually 2 times 3, which is 6 unit that is covering for 10 liters. Okay, yeah, that's the problem you mentioned. But why is this confusion arising? That's what I'm saying. It's not 3 red that is giving 10 liters. It is 2 times red, which is giving the number of units, which is 2 times 3, which is 6 red, which is giving actually 10 liters of paint. And what was the other? 4 times 1, which is giving 10, finally 10 liters of paint. So this should somehow come. So seeing how many units. So what I'm trying to say is R, B, Y do not capture the final amount of units that you are.
So can this R be the quantity of the red color in 1 unit?
Can R be the quantity of
red in 1 unit, in 1 unit of R?
Yeah, right. So R can no. R is not one quantity in 1 liter of paint. That's what you're saying?
No, not liter, but then the R here may refer to the quantity in 1 unit. Like it's quite possible that 1 unit of red color equals to say 900 gram, and whereas 1 unit of the blue color may equals to 400 grams in that sense.
Now, but yeah, that's making it more complicated. That's what I think. Can you talk in terms of units or liters, not grams?
Yes. Liters. So here the meaning of R would be how many liters of the red color is there in 1 unit. And that we require.
No, but yeah. But now that is slightly dangerous because now you need a relationship between units of red and liters of red.
Yes. So okay. So I need say 2 boxes of the red color, and I don't know that how many liter is there in 1 box, right? So so in that sense probably, but then it's not necessary that all the boxes, the boxes of all the colors should be of the same size. They may differ. That is how we forming the linear equations. The values of these quantities should differ, R, B, and then Y. So to produce 10 liter of something, I would be requiring 2 boxes of filled with the red color. I do not know the size of each box of the red color. And then I have 1 box of the blue color. I don't know its size. So basically, by solving these equations, we are trying to determine what are the sizes of the boxes of the individual colors.
Okay. Yeah. The Guru, you were raising your hand.
Sir, I don't have any exact way to move ahead, but what I felt was in equation 1, whatever we have on our left side is equal to 1 liter of paint. So why don't we scale up this whole thing, multiply it by 10, multiply it by 5, multiply it by 8 on the left hand side?
Okay.
Which ultimately means 10 liters, right? So we can answer how many units of red, blue, yellow we need at the end. Instead of
but what will be on the right hand side?
Liters.
But what will be on the right hand side?
Liters, 10 liters.
And on the left, you'll multiply it by 10. Okay. Wait. That will be actually. So what you are saying is 10 times this amount is equal to 10. That's a bit different. That's a bit flawed because you make it homogeneous. Because if I multiply by 10 here, these will get cancelled, and then you have 2r plus 1b equals 0, which is still fine, I think. Yeah.
Hello.
It's not equal to 0. It will be equal to 1.
Hello.
Which will be equal to 1. Yeah, actually, this is still fine. Good. Yeah. Yes, Satendra.
Hello.
Yeah.
So what I'm visualizing, if you take, if you equate 2, 1, 0, 0, 3, 1, I'm taking a matrix, 1, 0, 4. That is of the colors.
Okay, wait 1 moment. 2, 1, 0, 0, 3, 1.
1, 0, 4.
Okay.
This represents the color.
Okay.
That is equivalent to 1, 1, 1. If I can write that this is equivalent to 1, 1, 1 matrix.
What do you mean this is equivalent to 1, 1, 1?
Means that is of colors, all 3 colors, because this combination is equal to
first row represents of one color, that is 1 unit. This I'm taking as 1 liter of first row represents 1 liter of the first color.
That's
one.
right. That's right.
Second column represents the 1 liter
1
of
liter
the
of second color.
Yeah. And third row represents the third color, 1 liter of the third color.
That's right.
Okay. So can we equate equal to 1 1 1 something like matrix?
So you can't equate it to 1 1 1 because they are clearly not same.
I'm getting. I'm telling this one. Here is a matrix, and what I'm visualizing, that is 1 1 1 unit. Okay. Now that we have 1 1 1 matrix. Okay. So that I have to 1 1 1 column matrix, that I have to transform into 10 5 and 8. Hello.
Yeah.
This I have to transform into 10 5 and 8. So now what I have to do, I have to convert 1 1 matrix to 10 5 8. To do so, I have to multiply this 1 1 1 column matrix with 10 0 0 0 5 0.
But separately you will need to do that, no?
Oh yeah, no, not row wise, not this side.
Okay.
Equal to means
like this.
Into this I'll represent as a matrix into X. Let's represent into X.
But
this matrix.
Yeah, okay.
Okay, this into X. Write it, sir. I'm telling. This into X.
This
2
into
1 0.
This into
2
X.
1 0.
Like this.
This into X. Equal to this. You erase it. 10 5 8. Erase it.
Okay. 10 5 8. Erase it.
Now we'll take a matrix 10 0 0 row wise.
Okay, 10 0 0.
Next will be 0 5 0.
0 5 0.
And last will be 0 0 8.
Okay.
Into 1 1 1. That matrix multiplied by 1 1 1.
Okay. But what is this achieving?
It's achieving that key. Okay, now how many units of red and that all will get equal to this? I think same thing will get. No? 10 5 8. We'll get the same equation, I think so.
See, if you multiply, okay, when you multiply 10 by this,
we'll get the same thing, I think.
We'll get 10 5 8 only, you know.
10 5 8 only we'll get.
And yeah,
we'll
but
find
see,
X.
it's about finding X, no? Okay, this I'll remove.
Okay.
It's about finding X, no? And this is same as this, no?
This is same.
These two are same, right?
So we are getting in the fractions only, that part.
Yeah.
I've solved it. We are not getting exactly in the units. We are getting in the fractions only.
That's
like
right.
34 by 25, something like that we are getting.
That's right. Good. So I think what Guru suggested will work, but you will get the answer in terms of liters, not units. Okay. What Guru is suggesting is that anyway, so there is a confusion between unit and liters. So we'll scale it all to liters by saying that this guy is 1 liter, and I'll multiply by 10 to say 10 liters of this guy is equal to 10 liters. Okay, which means the same thing. And then this will cancel out to give 1, and then you have 2r plus 1b equals 1. An alternative proposal, that's what you were talking about, right, Guru?
Yes, actually, yeah.
Your screen is not visible, sir.
Oh no, really?
Yeah.
Okay, one moment. I'll broadcast again. Okay. Okay, no? Visible?
Okay, sir.
Yeah.
Yes, sir.
Okay, good. And
excuse me.
oh yeah.
Can I think I'll second Guru's solution on this one, but can we look at a simpler solution, like say I still am not I'm not I still haven't understood what the problem is with this question exactly, but I'll try to articulate what I'm thinking.
Okay.
It says that we need 2 buckets of red, 1 bucket of blue, and no bucket of yellow to make just 1 liter of paint color 1.
Correct.
So can't we just say that in order to make 10 liters of paint color 1, we would need whatever we need for 1 liter, we need 10 times that for each individual color. So 20 buckets of red, 2 into 10 buckets of red, 10 into 1 buckets of blue, and 0 into 10 buckets of yellow.
That is right. Yeah.
We can get thus we'll get individually the number of buckets of red, blue, and yellow for each equation.
That's right.
And this is similar to the one you were mentioning, like we have to multiply 10 on this side, means the initial equation 2r plus 1b plus 0y is equal to 1. And if we multiply that with 10, then we'll get 10 liters. So I'm basically trying to suggest that. So it's possible.
That is correct. Okay, but yeah, this is something I want to think about in Guru's approach also. But your approach also, thinking about, okay, I want to make 10 liters of this paint. So what I'll just do is 10 times 2 unit of 2 liters, 10 times 2 liters of red and 1 times 10 liters of blue will do the job, right?
Yes, I'm saying that only.
And next, what will you do? Next, you will do 5 times 3 liters of blue and 5 times 1 liter of yellow will do the job for the second color.
Yeah, exactly.
And that same you will multiply with 8. Now, what I'm trying to say is the total amount of red, blue, and yellow you come up with may not be the optimum amount.
Okay, so we need to find the optimized amount here.
Yeah, how many units do you want at least? Okay, because see, there are these extra constraints. No, you want red, blue, yellow that will satisfy all these 3 equations.
Hello.
Yeah.
Sir, is it 28 units of red color is required and 35 units of your blue color and 37 units of yellow color is required to get this result?
Oh, yeah, I'll need to check that out. The final solution.
Okay, what I did actually, I took it as a simple way. I have considered like 1 liter of color 1 requires 2 buckets of red, 1 bucket of blue. Like 1 liter of this requires 2 units of red and 1 unit of blue and 0 units of yellow. It means if in 1 liter of color 1, this proportion is fixed. So now I have to make it as 10 liters.
Right.
So what I did, I multiplied by 10.
That's that's what Guru was suggesting also, and Amlan was also talking about. Yeah.
So I got 20 units of red.
Yeah.
10 units of blue and 0 units of yellow.
Right.
And in the same scenario, for the color 2, I've got 0, 15 and 5. And for the color 3, I've got 8, 0 and 32. So basically the question has asked that how many units of base color is required. So I've added the red column only. The red column comes out to be 28. And the blue comes out to be, this is 25. I think, and the last one comes out to be 37, something like this we'll get. Because I think it,
I mean, I mean, so far I don't see an outright problem with this approach. Okay, so far. This may be actually the fix for it. Okay, I mean, the other way to do it would be, I mean, that's what I was thinking about earlier, was when you come up with the you don't multiply with 10 or whatever. Okay, what you'll do is, let's say you come up with r equals 3 and b equals 4, you'll just plug in 3 and plug in 4. So 3 times 2, that's what you will do. and when you have 4 here, 4 times 1, that's what you'll do it for each equation. That would be the more intuitive thing to do, because when I actually imagine the units of the 10 liters of paint required, that's what is actually happening, right? You have 3 units of red for each of the 10 liters that you have. What you'll do is you'll just multiply that R by 2, and the same thing. That's what you'll do. That's the way in which I was imagining. Whether these two approaches are equivalent or not, I'll need to think about it. Okay.
Sir,
Yeah, I'll just take one. Yeah,
by
last
this
question.
approach, we are getting the answers of the red in the fractions only. So we are not getting
No.
proper constraints
Oh, okay.
by this
Is
approach.
that so? By which approach?
By this system of equation we are doing. So by that we are getting the answers something in fractions. Like we are not getting the exact that part.
So when you
proportionality-
solve this directly, you're getting fractions, is it?
Yeah, sir. That only I'm saying.
Oh,
And
okay, okay. Okay, that is actually a good point. But fractions is not a problem, no?
Excuse me, sir.
Yeah.
Sir, can you just scroll up the question a bit? I need
Okay.
to just confirm one thing. Sir, it has not asked for. Has it asked for an optimized solution here?
It has not.
if it has- so then why are we treating it like as a system of linear equations? Why do we need to find the point where all these? What do we find in a system of linear equations? Something that satisfies all three equations,
That's
right?
right.
So, in a typical scenario, we'll find a point that satisfies both the x and y equations.
Right.
But why are we doing that here? I don't think that
You
we
mean
need to find.
they may not be asking about an optimized solution. That's what you're saying, no?
Yeah. They
Ah.
might just simply be asking that we need 10 of this one, this color, we need 5 of this color, we need 8 of this color, which simply makes it a normal question of ratio and proportions.
I know, but see,
Might be.
why should we optimize it? Because I can answer this question by saying that take 1 million units of red, 1 million units of blue, and 1 million units of yellow.
Yeah, that's also right.
Right. So it's a perfectly good answer if you don't take optimization into consideration. Right. So that's why if you look at a question like this, then it automatically means you want to optimize.
I have a small point here.
Yeah, well.
So is the real problem is that the problem is so simple that this is not even a problem to be solved as a set of the linear equations. This is not a problem of the linear algebra at all. Is this the problem of this problem? Because this problem seems to be a simple arithmetic problem. The Sarinder said that we require 28 liters, units of the red and the other quantities. That's so, and probably unnecessarily, we are trying to form the equations from the problem. And whereas this problem is a problem of simple arithmetic. That for 1 liter of the construction, we require this composition. Then, how much units of red are required for 10 liters? 20 units. And how much red are required for the color 2? 0. How many units are required of red for the color 3? Say 1. So then for the 5 units, 8 units, I require 8 units of the red. So in total, I require just 28 units of the red to create 10 liters of the color 1, 5 liters of the color 2, and this one.
That is true. That is true. It is actually simple in this formulation. Okay, I understand what is the problem with the question now. Okay. I finally understand what was wrong with the question. Okay. Why it requires linear algebra. Okay. And yeah, I have to admit, like the way it is written is very stupid. So this needs to be produce any of or either. So either either 10 liters of paint color 1 or 5 liters of paint color 2 or 8 liters of paint color 3. Only this will actually solve the problem. Just come up with a set of units that will satisfy 10 unit of paint color, 5 liters of paint color 2, and 8 liters of paint color 3.
Yes, yes,
Right?
yes.
So this is where there is a constraint. This is where the lines must intersect so that they satisfy, all three of them. Taking the same unit of colors, you can make 10 liters of paint color 1 also. You can make 5 liters of paint color 2 also, 8 liters of paint color 3 also. I think this is the fix to the question, which will force us to use linear algebra actually. But that's the line in which.
Excuse me. Excuse me. I did get your intuition here. You
Right?
said, I think we understand the issue now. But I just plugged in those numbers into my calculator.
Okay.
I got the answer of red. It has given me in a decimal. I can convert it into a fraction.
That's okay.
It's actually 108 by 25 for red, and
Okay.
34 by 25.
34 by 25 for blue,
Okay.
and the third Z is 23 by 25.
That's right. Okay. But 25. Okay. Okay.
So I think your intuition might be right here. They are simply asking either or.
Yeah.
What is needed to produce either?
Yeah. Because otherwise, like Goel said, there's no need to apply linear algebra. Yes, Satinder, you have raised your hand.
No, just by mistake. I'm
okay.
saying, sir, the problem is simple only. That is actually they are talking about color 1, so maybe it is of 1 liter only they are talking about.
No.
Because
they are talking about, I want to achieve a set of the number of units of red, blue, and yellow. Okay, with which I can either make 10 liters of paint color 1, or I don't make paint color 1 at all. I make 5 liters of paint color. Yeah.
Okay. So here is the problem that when you are using 2 units of red and 1 unit of blue and 0 units of yellow, so how much unit of color you are making? That color 1, that proportion must be something, no? Then only we can come to know.
Right.
That by mixing, you are getting 5 grams, 10 grams, or 1 liter or something.
That's right.
So we can't go with the system of linear equation also, and
No,
we
no.
can't go with the proportion also.
No, we are using system of linear equations
Okay.
to come up with this. Right.
Okay.
Or, sir, how about we doing it like this?
Yeah.
Like we take it as a system of linear equations where 2r plus 1b plus 0 is equal to 1, 0r plus 3b plus 1y is equal to 1, 1r plus 0b plus 4y is equal to 1.
1. Okay.
So this thing will become into a 3. It will become a 3 by 3 matrix where 2 1 0 0 3 1 1 0 4 into a singular column matrix. RBY is equal to 1 1 1.
Okay.
Now, since we need 10 liters of first color, the first row, 5 liters of the second row, 8 liters of third row, why don't we multiply both the sides with another 3 by 3 matrix, 10 0 0 0 5 0 0 0 8.
You will get the same answer, sir. You will get the same equation. You will get.
And then we'll end up with 25 0 0 15 8 10 0 32 is equal to 10 5 8.
Excuse me, sir. I'd like to say something here. What Guru suggested here, his answer is quite valid, but again, basically, if sir, we are saying that 2r plus 1b plus 0y is equal to 1, and then we are multiplying it with a matrix that will basically multiply the entire equation with 10. Aren't we saying that, we are not considering r, b, and y as variables? We are just considering it as proportions. They will lose their meanings if we just multiply with the entire equation with 10. Will r, b, and y not lose their meanings? Because here we are just solving it like a proportion. I mean, the answer will be the same to the proportion one.
See, first of all, I'm not sure what. Okay, so what Guru you're proposing is take 210.
Yeah, 031
031
104
104
into the singular column matrix RBY.
times, okay, RBY, okay,
is equal to 1 liter, 1 liter, 1 liter.
okay, okay,
And
okay.
multiply both sides with a 3 by 3 matrix 10, 0, 0, 0, 5, 0, 0, 0, 8.
So what you're doing is 10, 0, 0,
0,
okay,
5,
okay.
0, 0, 0, 8.
0, 0, 8, okay. And so you'll also multiply in the left, no?
Yeah.
By 10, 0, 0, 0, 5, 8, 0, 0, 5, 0, 0, 0, 8. And here what you are doing is putting 1, 1, 1. No?
Yeah.
And RBY are the unknowns. So what you did was you multiply the entire top by 10. So first what you are saying is, um, so before I multiply by 10, 0, 0, what you are saying is, okay, these amounts, I want to figure out the number of red, number of blue, number of Y I need to form um, form 10 liters
10 liters, 5 liters, and
of
8
color
liters.
1, 5 liters color 2, and 8 liters color 3. Okay. I don't think these two methods are equivalent. I mean, directly solving them, because here you'll get 10, 5, 8. That is fine.
Yeah.
Here you'll get something else, no?
Yeah, yeah.
So what happens here is you are first finding out how much of, okay, so this is the difference between the two approaches. Your approach would say you to find 1 liter of each color, okay, how much yeah, so to make 1 liter of either color 1 or color 2 or color 3, what is the proportion of red, blue, yellow you would get, right?
Yeah.
And now what will you do? This is just giving how much red, blue, yellow. Then you are saying multiply by 10. Is that not? So matrix multiplication is still associative. So that's what you are doing first here. 2R, B, and so on. Then what you are doing, you are multiplying by 10. Now what you are saying is um, um, multiply by 10 to the first equation, and you will get 10 on the right hand side.
It's like 25, 0, 0, 15, 8, 10, 0, 32.
Right. So are these two equivalent? No, it does not look like it's equivalent. See, because this approach of directly solving them says to get 10 liters, 5 liters, 8 liters, what are the amount, or 10 liters of color 1, 5 liters of color 2, or 8 liters of color 3, what are the amounts of red and blue I need? Red, blue, yellow I need, units of. Here what you are saying is to get 1 liter, okay, first you are saying to get 1 liter of color 1 or 1 liter of color 2 or 1 liter of color 3,
Yeah.
how much of red, blue, yellow do I need?
Yeah.
And then multiplying it by 10, 5, 8. Okay.
Yeah.
That seems a bit different. I don't know whether this will be as optimal as the previous one, because then you can scale it up to any other amount of units, right? Okay, but I'll check this out. I'll check this out. I don't think these two are the same. Okay. I'll check this out. Because it's actually quite late also. It's 10:40. So we need to close soon. The cutoff is at 8 actually. Yeah, but I'll okay, good. I'll look into this. Okay, Amlan?
Okay.
Yeah.
Okay, let's just do final. Yeah, Guru?
Nothing, sir.
Okay. And Koel, you were saying something?
No, just a small point that if we are solving a set of the linear equations, does this mean that all the conditions should get satisfied simultaneously, or is there an option of taking the or off like you did here, either or kind of the situation?
Okay. So actually either or is representing simultaneously, because before the way I was interpreting it or was that we are going to add all these values, but that does not make sense. That does not require a linear algebraic approach, right? What we are saying is, given that same amount of units, either I can do 10 liters of paint color 1, 5 liters of paint color 2, 8 liters of paint color 3, which means that is a point, okay, a point in the 3D space, okay, point in 3D space, which is x some r by, okay, which is satisfying these three lines, and this line represents 2x plus 2r plus 1b, 2r plus 1b equals 10, and this line represents the other guy. This line represents. This is the point where either I can always make 10 liters. This is the line where I can make 10 liters of color 1. This is the line where I can make 10 liters, 5 liters of color 2. And this is the line where I can make 8 liters of color 3. Right? So if I stay at this point, it means that at any time I can make 10 liters of color 1 with this RBY amounts of red, blue, white, yellow, which will finish everything. Finish red, which will, because since it is in the line, I won't have anything residual, right? I'll use all of my red, all of my blue, all of my yellow, but definitely I'll get exactly 10. Or with that same amount of RBY, I can stay in this, choose to stay in this line. Okay, which means I can make color 2, or I can make 8 liters of color 3. Yeah, who is speaking that time?
So an intersection point means something which satisfies all the three equations.
Exactly, satisfies all three. But in English, that's the interpretation that I'm making, that I can make either color 1 or color 2 or color 3.
Oh, I see. That's
okay.
Fine. So, thanks.
Okay, so is that fine? It's 8:42 already, so I'll discuss this in the next session. Okay, and yeah, is that fine, everyone? Goel, Kishore,
Yes, sir.
Amlan, Guru.
Yes, fine.
Okay.
Okay, sir.
Okay, Satinder.
Okay, so thank you, sir. We'll discuss next session.
Sure. Okay.
Sir, before you go,
What then?
before you go, can you tell us, sir, which institute do you study or work at?
Oh, okay. I am currently in IIT Madras. I'm doing a PhD in computer science. Okay, and yeah, my field is called complexity theory, computational complexity theory. So yeah, I think Goel is crediting that course in NPTEL also, right? So yeah, I think he'll be able to tell you what is there, and so what else shall I tell?
I have actually heard about complexity theory.
Oh, great. Okay.
There's a great course by Santa Fe Institute also, I think.
Oh, nice. Okay, great.
Santa Fe Institute has a great course on this complexity theory for general people.
So Amran, there are two types of the complexity, in fact. So SFI deals with the complexity in a different way. And this is the complexity theory wherein we study the different complexity classes. So, I mean, those two areas are slightly different. In the Santa Fe Institute's complexity theory, they talks about the complexity from the viewpoint of the evolution, right? Complexity in general, diversity, complexity, evolution, emergence viewpoint. And whereas in this computational complexity course, we study the complexity classes. So this is like difference.
Okay.
I got it. Thank you, sir.
Yeah. I mean,
so
I
one
think.
last
Oh, sorry. Yeah, Guru.
Is Stephen Fredberg's book good for this course?
Oh yeah, definitely. I think I think that book deals Okay, that's not the one. Yeah, that is perfectly fine. I think that has a good geometric flavor to it. There is another book. I forgot the name. Okay, it's a long time. But there is a book that talks about linear algebra without ever mentioning determinants. I mean, next week you'll see what determinants are and so on. Maybe you've seen it in high school, but that is. I'll give the references next time. But yeah, Guru, that's completely fine. And it's just that I prefer Gilbert Strang, but I think there are there is an own set of references that is there in the course page. You should check that out too.
Okay.
Okay. Okay, I think that's all right. Nothing left.
Thank you, sir.
Okay, thank you.
Thank you, sir. Thanks, sir.
Okay, thank you, Amlan. Okay. Okay, bye.
Bye bye.
Okay, bye, Guru. Okay, Satya.
Thank you, sir. Bye, sir. Thank you,
Okay.
sir.
Yeah, thank you, Satyendra.
Good night. Good night. Good night, sir.
Good night. Good night. Meet you next week, Tuesday. Okay.
Okay, sir. Nice meeting you, sir. Thanks.
Okay. Bye.